We are back. Okay, so we're going to try to generalize things a little bit. So, if you have a multiple degree of freedom now system, we can't really focus on a certain natural frequency, of course, in a certain natural displacement configuration. We have multiple ones. So when we talk about an n degree of freedom system, of course, we can represent it as n natural frequencies and n modal vectors. We said that a natural mode of vibration is the frequency plus the vector. And depending on the initial conditions, as we just said, you can excite a certain mode. You can obtain to see a solution that only shows a certain frequency. Everything that we're going to do next is going to be valid for small displacements, small motion. So again, we can linearize things. So in other words, the equations that we have seen for the single two masses to spring system will continue to be valid in our assumption that the displacements are not that they're small. Okay. Things to remind ourselves: the mass matrix is always positive definite. Well, you can't have anything otherwise, because kinetic energy is always positive. That's a way to show it, but really we don't want anything that is a zero mass. The stiffness matrix instead can be positive definite or semi-definite as well. And you see semi-definite when the system admits rigid motion, which corresponds to a frequency of 0 and modes and rigid, everything is 0 basically. And when you have rigid body motion, the potential energy that has to do with elastic properties of the system is 0. Basically, there are springs, but like in this example, there is a spring, but the spring may be completely unperturbed, not compressed, not elongated, and the two masses are moving exactly the same way, and that's rigid motion. So in that case, for a system like this, you can show it to yourself that the stiffness matrix is semi-positive definitely. So it admits at 0 eigenvalue because the system admits as part of the modes, the mode that corresponds to omega equals 0. And that's what you would find if you've ever used the SolidWorks and other software tools that compute for you for a continuum. They do a finite element analysis. We'll see what that means. And they compute the natural frequencies and modes for your system. There's always, if your system is unconstrained, so if it's just a spacecraft, for example, without being constrained to anything else, free floating, it will give you some 0 frequencies because the system can undergo rigid motion. It's completely unconstrained. While that was not the case with the previous example where the mass M1 was attached to the wall. In that case, there's no possibility to do that. Well, first you have an additional spring, but also there's no rigid motion possible. Okay, so a few properties there. Damping, that's the one thing that we have left out so far, but it's worth introducing now that we have this compact form of writing linear equations, mass and stiffness matrix. We need to introduce the damping matrix. The reality is that structural damping is still something that we're not able to model that well other than through experimentation. Often is, in first approximation, neglected, but it's there. And really what you see is that given our limited knowledge and ability to model it, is that we just model this C matrix as a linear combination of the mass matrix and the stiffness matrix. And it kind of makes sense. A system is usually damped in different ways depending on its inertia, mass matrix, and its flexibility, which is the K matrix. But really, it boils down to experiments. And this is true for problems like tribology, like modeling of friction. We still are not able to model friction that well. And so we base our models on experimentation. There's the field of friction modeling is still it's still pretty active. So and this is a similar scenario where we have a phenomenon that is not completely well understood, and so we make this approximation. So if we include the C matrix and we do everything that we have done before through the exercise to decouple the dynamics, we find, we just, without going too much into the details here, we use the unity model masses normalization, and then the U transpose CU will become an A identity matrix because I've normalized the modes with the normalization that was the third one. Let me go back to that slide. In other words, we normalize the modes like this. U transpose MU is equal to 1. But since I have defined my C matrix as a linear combination of M and K, well, the part of this linear combination that corresponds to M, when I multiply, pre-multiply with by U transpose and then post-multiply with U, gives me the alpha identity matrix, and then I have another constant beta and the diagonal matrix of the frequency squared. We define usually 2 zeta omega as alpha plus beta omega squared, and we call this zeta the damping ratios. And so in the end, we get the classical spring damper equation for each of the Q variables that would look like this. And still you can decouple your equations. It's just that the zeta values have to be given to you when you solve the problem. So you need to be able to evaluate them experimentally by exciting the system and basically with a clock measuring how it's behaving. But you know, that's what we usually do. A note on normalizing the vectors through the mass matrix. You can use the eigenvalue or IEG command in MATLAB that gives you a unitary norm vectors. So if you do that in MATLAB, it will give you the U's that normalize by unitary model masses. And so if you go with MATLAB, it will not satisfy the mass normalization condition. So if you really want to normalize your modes with the masses, you can basically impose, remember that if UI is a model vector, also alpha UI is a model vector. So you can actually use some alpha UI, impose that this condition is respected, and solve for the alpha values. And then alpha UI will be the normalized unitary model masses vectors. So this is just a note to basically tell you that if you're obtaining your U model vectors through MATLAB with the eigenvalue command, which is really what you would like to do, because let me go back to our own example. Remember that this is the equation we're dealing with to find omegas and, where is it? Oh my goodness, I lost it. Give me 1 second and I will find it. Yeah, this equation 14 is the one that, you know, we set the determinant to be 0 and we find the omegas. Once you find the omegas, you basically solving, so basically here you're solving an eigenvalue problem to find the U's. So if you actually do this in MATLAB, just keep in mind that MATLAB is giving you already normalized unit eigenvectors. So they're kind of normalized with technique number 2, I believe, in my list. And so this is basically an operation that you want to do to actually find the model vectors with unitary model masses. That's all, just a small note. So now let's go to continuum, because we talked about 2 degrees of freedom. We talked about any degrees of freedom, kind of very high level, and we talked about adding the damping. But what happens to continuum systems? Well, the difference is that, first of all, with lump parameter systems, or LPS, discrete systems, you have a certain number of degrees of freedom. The displacement depends only on time, You have ordinary differential equations. So you can do what we've done so far. You find your mass matrix, K matrix, decouple the equations, find the omegas. All that we've seen is just that you have n modes. You have as many as your degrees of freedom. But still, it's manageable with the matrices and linear theory. Instead of continuous systems, a distributed parameter system, or DPS, you have infinite degrees of freedom. The displacement. So if you focus on a certain location of your structure, its displacement will depend on time and position at the same time. You have partial differential equations and boundary value problems. But there are similar concepts for distributed systems. You can talk about natural frequencies. You can talk about natural displacement configurations with now modal functions instead of modal vectors. And the modes of continuous systems are orthogonal, like the ones for discrete systems. And so the difficulty with these is that, again, they have partial differential equations, and you have very rarely exact solutions. While for the lumped parameter systems, which is everything that we have discussed so far, we obviously have closed form solutions. We have those beautiful oscillatory behaviors, maybe with some damping, but we can definitely deal with those. And so what do? Again, we are engineers. We take these continuous systems, which is really reality, what we actually have to deal with, and we discretize. We perform what is called finite element modeling analysis, and so we try to connect continuum with discrete. Okay, let's see what we do. So, as I said, for typical structure, the exact solution doesn't usually exist. You divide the structure in elements. That's why it's called finite element method. That they are connected by a finite number of points. They are called nodal points. The motion of these points is defined in terms of the nodal displacement with interpolating functions, and then basically you have to find for each element the stiffness as mass and mass matrix, and then you assemble, you connect the different elements through boundary conditions, and finally find the total mass and stiffness matrix for the system. So in other words, we're going to take a continuous system, and manipulate it so that we get the equation that you see below. Exactly what we have done so far. We want to eventually find a mass matrix and a K matrix, and the X vector is now these nodal point displacements, is the connections between the elements. So, for example, in this cantilevered beam, say that I have 1, 2, 3, 4, 5 elements, I will have 6 nodal points. The attachment point, connection between element 1 and 2, and so on and so forth, all the way to the N1. For the plate, same story. You can have 5 finite elements, and then you have all these connection points. And so in my representation, eventually, my mass matrix and K matrix will have to be found so that I can write an equation like this, where the X vector is the displacement, whatever that means, of each of these connection points. And displacement can be an XY translation plus a rotation. It can be many things. So each element can be associated with multiple coordinates. So talking about, in particular, the cantilevered beam, for example, or just the beam in general, we can start working on an example. Okay. So let's say that we have a uniform Euler-Bernoulli beam. We focus on one element and it's bending. So there is no, this is not, to the left is not necessarily the wall, actually. I mean, it's just that I'm focusing on a piece of this beam. So this is one element. And you see there is node 1 to the left, node 2 to the right. I use some Cartesian system X and Y to represent its deformation. And I call W1 and W2 the displacements along the Y-axis. And I don't really talk about rotations, I talk about slopes, represented by the value theta 1 and theta 2 at the nodes themselves. So By slope, I basically mean the dy dx, how it's, the slope of the midline at those locations, okay? And so for each of these elements, 1 and 2, I actually have two variables, w1, theta 1, w2, theta 2. That's all I'm allowing here, okay? And so I want to find the stiffness and mass matrices for these elements, and then eventually I have multiple elements and I need to connect them together. Okay. The assumption here is that the shear deformation is neglected. So that's why I call theta the slope, not really a rotation. And so and basically all I have to care about is the y or w deformation and that slope. That's why I started with that assumption. So the partial differential equation, we said that, that's what we have for continuous systems. Will look like the one at the bottom of this slide. It's a pretty ugly equation, but you have m, which is the linear density of the mass of the beam, the Young's modulus E, and then you have this I, which is the moment of inertia of the cross-sectional area about the z-axis through the center of the section. So in other words, go back to this image, see the z would be sticking out of the page. It's the moment of inertia of this little piece with respect to z, computed at the center of the element itself. Okay. So what do we do with that? Well, we know that the exact solution for that Euler-Bernoulli beam equation, in case it's clamped and free or cantilevered, so one side is attached to a wall and the other side is free, can be expressed as a function of position and time, separating the dependency of position and dependence of time like this. You can demonstrate that the f of t will look like what we've seen before, basically, an amplitude and a cosine law with a phase, while the y, the component of the solution that depends on position, has to satisfy this differential equation. The fourth derivative with respect to x is some beta to the fourth y of x. And we do know, again, this is known theory that goes beyond our scope here, that beta is basically given by this expression, omega squared MEI, and we in principle have infinite values of betas as we have infinite values of omegas for the section. And here we're showing the first three for the beam in particular. This equation, this differential equation here, has the following solution. So y of x, it's a combination of regular sinusoidal and cosinusoidal functions and also hyperbolic cosines and sines. And these are what we call the eigenfunctions. So before we had the function of time, or the modes, I'm sorry, the shapes, and here we have similar concept, is just another called eigenfunctions. So this would be the equivalent of your model vector, if you like. Okay, in particular, the first three eigenfunctions for that particular system will look like these, just for your knowledge. L will be the length of the beam. And so, going back to the way I want to discretize my system, my Q variable, or nodal displacement vector, I am imposing that has to be W1 theta 1, W2 theta 2. I care about these coordinates here. So the transversal displacement will be given by, well, what we've seen before, the function of x and time at the location 1 and location 2, of course. And so we have this L, which is what we found before, the shape function, or interpolating functions, and Q. Let's see. Yeah, so we're basically doing exactly what we've done before by separating a part that is a function of position and a part that is a function of time. And so we say that our variables W1 and 2 and theta 1 and 2 are functions of time, while these L functions are functions of where you are along the beam only. So what are these L1, L2, L3, L4? We'll see in a second. Well, we know that if we impose our solution to look like this, so keep in mind that so far I haven't used any of these yet, okay? This is the actual solution for the continuous case. I haven't used it yet. So now I'm going back to my lumped parameter system, and I want to have the y to look like this. So I'm imposing this. I'm separating time and space in a sense through these functions, and I don't know what these L are yet. But I do know that my y solution at location 0 and any time has to be W1. Location H, which is the length of my finite element, is W2. That its derivative, that prime means with respect to x, because it's the slope of the midline, is a location 0 is theta 1 of t, and a location H is theta 2 of t. If you take equation 2 and those conditions, so this equation that I've imposed and those conditions, I find that my interpolating functions will have these boundary conditions here, 0, 0, and h, both in terms of the functions themselves and their derivatives with respect to x. So each shape function has to satisfy 4 boundary conditions. We can use, for example, a third order polynomial. It's just a choice. And so for L1, it may look like this. This is L prime. And so imposing the boundary conditions, you can basically find the coefficients A1, 2, 3, and 4. You do the same for the other ones. And basically this will be your shape functions for this particular problem. Again, we're looking at one finite element, and all I'm doing so far is saying that I have 4 variables of interest: vertical displacement on the y and slope. I want them to look like this, and this is what I get in terms of interpolating functions. And now I'm going to use some of the theory that I've seen before. So I'm going to use kinetic energy and potential energy. The potential energy, we know that for the element can be expressed as such an integral between the 0 position and the length of the element. And well, this is the integral form for the continuum problem. But I also want it to look like this, because I want to discretize my system. So this will be the continuum, E I of x, the second partial derivative of the y with respect to x. And I want it to look like 1 over 2 q transpose kq. Remember that q is this vector, w1, theta 1, w2, theta 2. Well, then, if you impose this equality, well, first of all, if I impose this equality and I plug in my solution, my imposed solution for the y, again, this is this one. There is a combination of shape functions and displacements. You can show that it will look like this: E I of x, the second derivative with respect to x of L, multiplies itself transpose, and then you have once you plug in your shape functions, you will have this final result for k. So this will give me, and it's a symmetric matrix, so what you see up here will be reproduced at the bottom. This will be my stiffness matrix of the beam element given by the finite element model. Okay. What am I doing here? Just to summarize, I know it's a lot of information, but I started from my beam. I know that this is my differential equation, and I know that in general this will be the solution in the continuum form, but I decide that I want to go with this. And so my yx of t, which in the continuum is given by this y of x and f of t, I'm gonna make it look like this. So I approximate my yx of t with this expression, but then what is the connection? The connection is here. In my potential energy expression, I still plug in what it will look like for the continuum. That's why I have the integral. But for the y, I use my representation of y. Okay. And so I get the stiffness matrix for a beam element as follows. And it depends, as you can see, mostly on the length of the beam, h, and the Young modulus and its moment of inertia about the z-axis. A similar type of approach would be followed by with the kinetic energy. I know that in the continuum is 1/2 the integral between 0 and m of the mass that is a function of x and the partial of the y function with respect to time squared. But now I have my L functions, and so I can, and I want this to be looking like 1/2 q dot transpose m, which I need to find q dot. So using my shape functions, eventually I can find the mass matrix that looks like this. And now this is a function of the length of the beam and its mass, as you can imagine. So this is the mass matrix for the beam element given by this finite element representation. Is this making sense, what I'm doing? I have a beam whose continuum behavior can be represented by solutions that look like this. If you like a shape part, there is a function of x given by these ugly sines, cosines, cosine hyperbolic, sine hyperbolic expressions, and then a function of time, which is a cosinusoidal behavior. But then I switched and I said, okay, I only care about these 4 variables, and I impose my solution, the same basically, but it's now only a function of the shape functions L, 1, 2, 3, and 4, and the displacements at those nodes. And from there, I can compute my stiffness matrix and mass matrix by imposing equality of potential energy and kinetic energy expressed in the continuum and in the discrete. Okay, so basically, let's see what we've done. We looked at a single element and found m and k for the single element. Now, my actual structure will have multiple elements, and we want to find an overall m and k matrices, and we do that enforcing boundary conditions at the nodes. So each element will be connected to the next one, and so on and so forth. So they can't move independently. So the W2, for example, will be connected to another. At that node, you will be connected with another beam, and so that displacement will be the same for both nodes when they touch each other. In addition, a coordinate system is required to go from the single element frame to a global reference. And so we have an example next that hopefully will clarify the process. It's a pretty simple example. Now, the bottom line is that no one does this by hands, okay? Nastran, SolidWorks, the software that does this. But, you know, it's important to understand what's behind you giving a SolidWorks a model and SolidWorks giving you the frequencies, because that's what it does. If you have a model of a spacecraft and you enter it into SolidWorks and you tell it to compute the first 10 modes, this is exactly what it's going to do. It's going to compute a mass and K matrix, and you can output those as well using an approach like this. So let's look at this particular example. It's a cantilevered L-shaped system. We have, let's see, 1, 2, 3, 4 elements and 5 nodes. Node 1 is the connection of element 1 with the ground, with the wall. Node 2 is connecting element 1 and 2, and so on and so forth. And so for each mode we have, for each node or element, rather, yeah, for each element, I'm sorry, we have a mass and a moment of inertia. And for each node, also we have a displacement and a slope. Let's see. So we have 4 beams, elements, 5 node points, and okay, no, here we are concentrating the masses at the nodes. So we actually have 5 masses and 5 moments of inertia. That makes sense. Now, different thing with respect to the other one. We have now both a W, which is the displacement, vertical displacement on the Y, but we also have the U, which is the displacement on the X. And we only want bending in the plane of the figure. And we're going to try to find the mass and stiffness matrices for the structure. Okay. All right, so the first step is you, well, visually analyze the structure. The boundary conditions are the following. We know that at the location 1, well, that's connected to the ground rigidly, so everything is 0. W1, U1, theta 1, 0. Since it's only bending, remember the assumption we made, the X displacement for the element, the node 2 and 3 on the X are 0. So there's no elongation in that direction, it's only bending. And then everything else that we know is only that W3, 4, and 5 have to be the same. So this piece is only translating vertically. Well, that is translating vertically the same way. So this is the note here. For the motion along Y, this substructure is acting as a rigid body because it's bending. So it can bend in the X direction, but in terms of the Y, the W3, 4, and 5 are all the same. That's the assumption of bending. Bending only. Okay, step 3. Consider the stiffness matrix for each sub-element with the same assumption that we had before. So let's see, for each element, we have a W to the left and a theta to the left, which is the 1 and 1, and then the 1 to the right, which is 2 and 2, which will be the Q's associated with that element. And so the stiffness matrix will be, something to be found. It's a field matrix. For example, for the element number 1, I'm stating here that basically the W1 and W2 components do not contribute in any way, so I have a bunch of zeros. And that is because of the boundary conditions, right? We delete those rows and columns because they do not contribute to the kinetic energy. They cannot change. Omega 1 and theta 1 were set to be 0 at all times. And so you're only left with this. For the second one, now the second element, go back to the image here. Element 2, the left-hand side is the node 2 and the right-hand side is the node 3. I definitely have everything. Everything can move and can contribute to the potential energy in principle. So we retain everything. For the third element, now again we switch coordinates in a sense. The contributions are due to deformations along the X. Remember that piece that points down has omega 3, 4, and 5. They're all the same. So there's no contribution. There's no deformation in that direction. It moves like a rigid body. So now we're focusing around the X deformation. And so for element number 3, let's see. we have the stiffness matrix that doesn't have the first column and row because they do not contribute to the overall potential energy, U3. So let's look at the boundary conditions. Remember, U3 is 0. That's the boundary condition. And so that's why I am removing these two lines in the matrix. Fourth element, you keep everything. The boundary conditions don't tell you that any of these variables have to go to 0 at all times. And finally, you consider the vector of nodal displacements for the overall structure, taking into account the boundary conditions, and you assemble the matrix for from each subelement into the final stiffness matrix. Okay. So remember that I color-coded the matrices, and remember that this is linearizing the system. So you start from this one, then you have this one, you have 4 of them, and you have to put them all together. So what you do is that you write in order your displacements, starting from the first one. Remember the first variables, omega 1 and theta 1 and u1, they're just the wall, so they don't make any contribution. So you start from 2, w2 theta 2, w3 theta 3, and then you have u4 theta 4, u5 theta 5. You do the same here, and you go back to these original matrices, and in each location that corresponds to the crossing of 2 of these variables, you enter the corresponding k value. Okay, so you basically add them together, and this is possible because we're linearizing, superposition is valid, and so this is what it's going to look like when you assemble it together. Okay, and this is for k. For the mass matrix, we're talking about now kinetic energy. So you're going to talk about time derivatives of the variables, okay? And the similar kind of reasoning applies. I don't have the individual slides to do the same exercise, but basically you assemble the single mass matrices. I think there is a typo here, into the total mass matrix, okay? Oops. So the steps are exactly the same, except now you have the time derivatives of the variables, and you add together the contributions of the single matrices into the corresponding elements here. So this is not something that I recommend anyone does by hands, because it's extremely annoying and painful. It is done for you for complicated structures, as I said, in software. And keep in mind that this is a very simple example, and it's pretty involving by itself. But it is important to know that at the end of the day, you are going to obtain an equation that will look like this, where now the x's for this problem are the w1 theta 1, w2 theta 2, etc. So you have a pretty big vector that you have to deal with, and this is attached to a wall. Imagine when this is actually a component of your satellite. So the wall is actually a rigid body that used to behave like the equations that we see in Euler's equations, and now you have these additional degrees of freedom that you need to deal with. So I think I'm gonna stop here for this topic. I would like to show you real quick how people may decide to represent the coupling of these with spacecraft motion. Just give me a second. So one of the many papers you can find that have to do with attitude control and flexibility. Attitude maneuvering and vibration, reducing control of flexible spacecraft subject to actuator saturation and misalignment. Really what I want to point out is how they represent the motion. Okay, kinematics and dynamics of something that has flexible modes. Nothing new here about the quaternion kinematics. It's what we've seen before. But so this is how. Sorry.
You're not sharing.
Ooh, I'm not sharing. Thank you. So let's go back to the title. Okay. So yeah, this is one paper that we're trying to reproduce for research. Camilo, who will speak tomorrow, is actually working on this as well. But so attitude maneuver and vibration reducing control flexible spacecraft that has actuator saturation and misalignment. So what I wanted to point at is how you may find the equations of spacecraft attitude motion modified when you have flexible components. This is the quaternion kinematics, and that's nothing new. But the model of a flexible spacecraft can be expressed as this equation number 2. So the j omega dot is what you've seen before. The omega x j omega is what you've seen before. It will be on the left-hand side if you want. I think u is the control vector that you can exert with thrusters or whatever it is, and these disturbances. But then you have these additional terms. They have a theta delta transpose eta double dot and these delta transpose eta dot. And this eta satisfies this equation, this other differential equation. So omega is the spacecraft angular velocity in the body. Well, this is the cross product, symmetric matrix. Omega and eta is and eta is the modal coordinate vector of the flexible appendages, exactly what we have seen before. Delta is the coupling matrix between the flexible appendages and the rigid body. And then C and K denote the damping and stiffness matrices like we have seen today. So the K is, no surprise, is the diagonal matrix of the omega squared, and C is the 2 zeta, well, epsilon in this case, we called it zeta before, the damping coefficient that multiply the omegas. So as you can imagine, now you have an augmented dynamics. Before we had something like 2 without these eta variables in it. Now you can't solve for the motion of the spacecraft. So in other words, you can't solve for omega, for example, integrated numerically, unless you're solving for eta, and vice versa, because there is this omega component in this equation. So as you try to control the omega, you're going to excite. You're going to have an effect on the modes, eta, and as you have an effect on the modes, you have an effect on omega. So everything is coupled here. And so basically your equations of motion will be 2 and 3 together. You can't have just one. And so now the state vector has to be augmented as they do in the next in the rest of the paper. We don't need to go into the details of what they do here, but you have a much more complex system that you need to control. And by designing control laws in a certain way, you can decide whether you want to excite some of these motions or you want to keep them at bay. You want to not excite them. And so we will see one example for a single degree of freedom rotation. So a simplified example, because again, this becomes explosive, having to include flexible modes for complex systems in trade-off becomes intractable by hands, very tedious, and you're going to be prone to errors very quickly. But we can see an example that has to do with a single degree of freedom. So I'm going to post these as part of your, well, these are already posted. I'm going to actually add in the files this paper for today. Today is the 30th, right? So let me see. Yeah. Here, files. 1 second, and we'll continue. Okay, so you have it under the folder for March the 30th. You have this dynamics of flexible spacecraft 2 because I had other papers that I just showed you. Any questions, concerns? Okay. Do we want to continue on the homework? I think I'll spare you the next part of this, and we'll do it later maybe, or tomorrow. But yeah. So basically, I'm going to give you a quick peek at what we're going to do next. But not today, or I guess not now. So this is what's coming next. Feed-forward control of flexible systems. This is not even feedback, actually. But we're going to deal with a simplified problem, which is a Euler-Bernoulli beam with an attached tip mass at the end and a hub. So the green one will be your spacecraft, and it can only rotate about one axis. And there is a pretty flexible appendage at the end. I'm sorry, pretty flexible appendage and a mass at the tip. You know, we want to control that. So we'll do this, but let me show you in practice what this means. I need to find a couple of videos here to show you. 1 second. Can't find them. So I have them on my website. Oh. Nope. Give me a minute. Oh. Okay. I think I found it. Yes. Can you see it?
Yes.
Okay. See even in Italian. So these were experiments run at the Naval Postgraduate School when I was working there as a postdoc. And so this is exactly the scenario you have. This black system here will be your hub. This is the flexible appendage, and this is the mass at the end. Okay, and as you've seen, sorry that this is going a little too fast. This now, there is a command that will change the angle 45 degrees and with a torque of 20 Newton meters. It's just a bang bang approach. So you give maximum torque and then minimum torque the other way, and this is what you get. You are exciting definitely one mode that is making you oscillate a lot. So usually one thing to notice is that lower modes, lower frequencies correspond to bigger oscillations. Highest frequencies correspond to smaller oscillations. And so in the control of space structures, we're really concerned and afraid about low frequencies because they correspond to big deformations. While the technique that we're going to see, called input shaping, it's a controller that takes the bang bang profile, and this is feed forward. There's no feedback here. You just apply a control law blindly. But the second one, as you can see, is a little more intelligent. It does have some residual oscillation at the end, but it's definitely less. So what this did was, knowing the frequency of the first mode, or an approximation of it, some model, and reshaping the bang-bang to look a little different based on that frequency. And this allows you to reorient your end effector, if you like, the tip mass, with minimal or reduced oscillation. And I think there's more. This is now less torque, so the final result should be less intense for the bang-bang. Seems worse, actually. I wonder if the title is right. Anyways. So I remember when we ran these experiments, we had to stop increasing the torque because at some point the hub and the device keeping it to the table was not holding. The thing was almost falling apart. So this is a bigger reorientation, pi over 2. Yeah, almost breaking everything here. And this is how more intelligently you can do this. You can notice that there are some accelerations and stop, acceleration and stop. To basically what you're doing with this input shaping technique is you are exciting a motion and then killing it, exciting it and killing it. So you definitely use a little more intelligence, and that explains even more why it's important to be able to model these natural modes of oscillation in order to control them. Okay. So that's the technique that, at least high level, I would like to discuss with you, either this afternoon or tomorrow. By the way, tomorrow is the last day that we meet, so I'm hoping that at least from one of you, we're going to see a completed homework too, so that I have a little bit of peace of mind that you're all on the right track and you're not struggling too much. So do we have the kind lady who was working on the homework 2 yesterday?
Yes.
Would you mind continuing, or?
Sure. Okay,
And
so
we can stop at 15, so we can keep going for another 25 minutes because I left early.
okay.
And then go relax. In the meantime, I want to do these videos here.
Okay, so a first thing I was thinking is that in the function that we defined yesterday that outputs P and the matrix Q, maybe it is also convenient to have as an output delta, possibly.
Delta
So
will
the
be
determinant of C transposed.
Yeah.
Because then, okay, so. Okay, so now I actually have some doubts how to continue. So I was starting to write the function that returns the MED work. And obviously now I need omega error and the error quaternion. So now when we first obtained omega error, we used as a quaternion in order to write the DCM that gives me omega in the reference frame of the body of the spacecraft. The quaternion that came from the from the equation of motion, where we were not considering also the MEDs, right?
No, you should.
So I think that instead of this block, because this was the first time we wrote it, But instead of this block here as an input, I should have a quaternion that comes out of the omega body that we integrated.
Yes.
Okay,
Yes.
so what I should do, oh sorry, okay, this was my first doubt. So what I should do is to take this block that computes the quaternion. Okay. And to essentially okay, to use this omega here.
That's right.
I'll clean it up later.
No, it's fine. Take your time. There's no rush.
Okay. Then here, okay, so essentially I don't want this anymore. Probably I could also just delete this block, but for now I keep it. And now, so I need to take this quaternion here. Okay, so this will be Q of the body. And this is the one that we need to compute the DCM, sorry. Let me zoom a little bit. Okay. So it's this one. Right?
So yeah. So how do you use it in there?
Sorry?
I was wondering how you use that quaternion in that block.
In order to evaluate the DCM, the corresponding DCM, because when we obtained omega des, it was in the reference frame in DCI,
Yeah.
and then we needed to write in the reference frame of the body.
Yes.
So that both omega des and its derivative were in the reference frame of the body. And then I had already written a block that computes the difference between omega of the body and omega des to get omega d, sorry, omega error. Just let me check. Okay, no, it's the correct order. Okay. Okay, and so now I also started to write the equation for the external torque. So
you well, you haven't worked on that yet. We can do it later. The omega error and quaternion error. You can do that later. Yeah.
Yes, the quaternion error. I'm just confused on the which comes first. That's why that was my doubt. Okay. So in order, because now what I have is the quaternion of the body, that is now this one with the block that we just wrote. And we also had the desired quaternion. So now in order to have the error quaternion, so here it should be the, for the error quaternion, we should have first the quaternion of the body and then the desired quaternion, right? And then apply this equation here.
Yes.
Okay, so the matrix will be written with the desired quaternion because it is on the right.
So the way I have the, yes, the matrix has the side quaternion, and the vector is the quaternion of the spacecraft. Yes.
Okay, because I was not sure about that, so
Yeah.
I didn't.
You got that right. Yeah. Oh, and also keep in mind that in the actual final expression, the only thing that you care is the first three components of the error quaternion.
Yes, I need the vector. Yes.
That's fine. Then you can the thing and then just use the first three. Yeah. Perfect.
Okay, so now we need to write this function here. So. Okay. Then I swear that I will clean it up and make it more.
There is no rush to do anything now.
Okay. So yes, maybe we can directly output the vector E. So this is a function of the body quaternion and the desired quaternion. So what we do is to write the whole error quaternion, and now I need to write the matrix. Okay, so it should be, let me just copy this so that I don't have to write it. Okay. Component. Then we have the third component minus the second component and the first component, right?
Correct.
Okay. Then we have, no, sorry, minus third component. I'm gonna leave always the first component, and the second. Then here we have the second minus the first, fourth, and the third. And finally, the last row is minus the first, minus the second, minus the third, and the fourth. Oh, sorry. This times cube body.
Let me see. Checking against mine for oh yeah. Minus 2. I have a slightly different
Sorry, can you hear me?
yes, I'm looking at, for some reason I have a slightly different last column. I basically have minuses in the last column. I don't know why.
I am using this one here.
Yeah. 4, 3. Okay.
Okay.
No, you're right. Yep.
Okay. And then I need just the first three components. I want a vector. Q, E, 3. So this should be the error quaternion. Sorry, the vector, the vector part.
Yes.
Okay. And now, what I want is, okay, first, this one will go into the function that computes the immediate work. And here, what I need is the desired quaternion. Okay.
Oh, and the omega error is just the difference between the angular velocity.
Yes, is this function here.
Oh, you have it.
It's just omega body minus omega des.
I uploaded for tomorrow. There's a folder with tomorrow's data. I uploaded the paper that Camilo was able to present.
Ah, okay, thank you. Okay. Oh yeah. Sorry. Okay, so I need this one to go here. While for the body quaternion, we have this. Okay. And now, this was the last one that I was missing, is, all right, this one is going here. Okay. Okay, so this is the function that computes the immediate work. So as an input, we have the positive definite matrix K that we have in the initialized file. Then we have omega error that comes from the difference, the error vector, the J total, and that's why we kept it as an output. Then here we have omega desired dot, and it is the one coming from the numerical derivation, right?
Mm-hmm.
So it's the one that we obtained in the second block as the numerical derivative after matrix multiplying, obviously, so that we get it in the spacecraft reference frame. And then we have, okay, omega of the body and ESW. We just need the SJ's vectors, so we just need this matrix here, capital omega, the external torque that I initialized to 0, 0, 0. I don't know if then we want to use something different. The matrix B, because we put inside capital M MED also the term with gamma double dot. So we also need B and gamma double dot. And then here I used just the expression that we obtained from our computation. Okay, so now Okay, now it's my it's the second thing I am a little bit confused about, because we want the constraint minimum solution for eta. And so we need to define our weight matrix, and then we found that the solution, it should be here somewhere. The constraint solution was obtained for eta equal to this product times the external torque, what I call M. So now, what I don't understand is for gamma dot. So eta contains omega dot and the omega, the capital omegas dot and the gamma dots. And for the moment, we simply defined. We started by defining gamma and omega dot as constants, because then we wanted to consider some kind of signal. So now, if I write a block that I need, I don't know, some kind of feedback between these two. Okay, so okay, so just to write the function. Okay. So I don't know if I can. I just start to write the vector eta. Okay, maybe this and then. So it will be a function of. Sorry?
Yeah, you have all those matrices.
The weight matrices.
Yeah, the D, etc.
Yes, I already put them together in capital Q. Then I have, sorry, D. And I also need the weights and also mu. So I need WS0, WG0. That is simply WG. Maybe I can already call it WG. Mu and delta should be everything. Okay, probably the first thing to do is to define WS, that is WS0 times the exponential. I don't know how to write it. X, maybe. Will it work? Minus mu. Okay. So I'm really sorry, but I never used MATLAB, so I'm not used to. Okay, so these are the WS. And the WG instead are constants and are all the same, or also the the weights for the spin are all the same, so it's just a number. Okay, and we need to define the weight matrix. That will be a 6×3 matrix, right? Okay. So I don't know if I can write it in a more intelligent way. Sorry, but then we have 0, WS, 0, 0, 0, 0, and another 0. Oh, sorry, here I wrote. Then 0, 0, again WS, 0, 0, 0. Then we have the part with, sorry, is this wrong?
No, that's right.
Okay. So now I'm writing the part with 2, 3, 4, 5. 1, 2, 3, 4. Now here I wrote it wrong. Okay. 1, 2, 3, 4. WG. And 0, 0, 0, 0, 0, WG. Okay. I hope it's correct.
So I'm going to take a couple of minutes. You can definitely continue this afternoon. Okay?
Yes. So I stop sharing.
No, it's fine. A couple more minutes. Just looking at.
Okay.
Your 6 p.m. right? Yes.
Yes. No, it's 4 p.m.
No, but we.
Oh, the next lecture. Sorry. Okay. And so now eta will be capital W times Q transposed times the inverse of the product between Q, W, and Q transposed. And this was capital W, excuse me. And finally, we have the torque.
So yeah, we can start in a second, but it would be nice if, I don't know if you have time, if for this afternoon you have something that we can try to run.
Yes.
Maybe. Not a must, okay, if you have time.
The problem is that I'm not really sure on how to continue because up to this point, I'm not sure on how to make the feedback.
Right, so eta is your feedback. The first components, yeah, look at the description of eta and you will see that they go inside the blocks that the C matrices. So the gammas will go there, and they will put together the C matrices and the G, S, and T vectors. And so the gammas will go there. The omega dots and the gammas and the time derivatives of gammas, etc., will go into the dynamics block as well, right?
So what I should do is simply to take the output that comes from this function, obviously split it for gamma dot and omega dot, and then use that again as an input for all the other functions.
And you may need to integrate them numerically as well, because I think there are some parts that
yes. Because now we simply put when we did it the first time, we put two constants and then we integrated and also the derivative. Okay.
All right, we'll see you at 6. We'll continue from here. Okay,
see you later.
Okay, bye.
Okay, thanks.
Bye.
Ciao.